Alright, so talking about constructive and destructive interference, we end up coming up with this experiment. It's called the double slit experiment. And it's using light, a monochromic light, which means that it's light of the exact same color, or if we know that color is related to frequency, of the exact same frequency, and having that light interact with itself to create what we call interference patterns. Now, an interference pattern, and I'm going to draw it on this quadrant, not down on this quadrant, is something that looks like this. So you get a peak at the center, and then you get a dark spot. You get a bright spot, a dark spot, a bright spot, a dark spot, and on and on and on. So what you end up doing is you end up putting a piece of film here, and as light strikes that film, it develops it, giving this band of bright, and then dark, and then bright, and then dark, then bright, then dark, then bright, and on and on and on. Okay? So what's happening in order to produce that phenomenon is that you're creating waves that are going through these two holes. So you're creating a wave that goes through these two holes, and as it goes through the holes, they start making these circular wave fronts. And those circular wave fronts start to interfere with each other. Okay? They do both constructive and destructive interference. So this point right here is going to be a point of constructive interference, where this point here is going to be destructive interference. Okay, so the dark spots are going to be destructive, the bright spots are going to be constructive. Cool? Alright, so as we go back and we deal with some of these ideas of constructive and destructive interference, I'm going to draw the path that two photons travel. They go through this wave, they interfere, and then we have these two streams of light that are coming through. They're going to come through, and they're going to strike that one point. And we're going to claim that that one point is a constructive interference. It's going to make a bright spot here. It's just the claim I'm going to make. Okay? Cool? So the path, the length that that object is going to travel is from here to here, and we're going to call that R1. Okay? The path that the second beam of light is going to travel is from here to here, and we're going to call that R2. Okay? It turns out that R1 and R2 have some sort of relationship between them. R2 obviously is traveling a greater distance than R1. Okay? So what I want to do is I want to relate R2 to R1 in a way in which I can simplify my problem. So first thing I realize is that when this line intersects this imaginary line, which is a line that's drawn perpendicular to the barrier to the screen, it creates an angle theta. Okay? So right here is an angle theta. Cool? Well, that angle theta is reflected here in this small area. There's a little piece here. This gap in between here, between the two slits, is a distance. And that creates an angle here, theta, so that there's a small section here that's going to be equal to d, the distance in between the slots, times the sine of that angle. Okay, so d sine theta. So this small section right here turns out to be d sine theta. Cool? Now R2 is composed of R1 plus that d sine theta. Cool? So this section right here, this R2, is R1 plus that d sine theta. Alright? Is that okay? So R2 is R1 plus d sine theta. So in order to get constructive interference, what does the length of d sine theta have to be? Well, that length has to be some number, and we're just going to call it m, times the wavelength. And what I mean by some number, I mean some integer. 1, 2, 3. Which means that this distance here has to be a full wavelength or 2 full wavelengths or 3 full wavelengths in order to get constructive interference, or even 0 full wavelengths if you want to talk about the center point. Okay? So if this distance right here is a wavelength, or 2 or 3 or 4, then when these two beams of light intersect at that screen, then I have constructive interference. Then I have a bright spot. Cool? So that means that d sine theta, in the case of constructive interference, I'm going to erase this, is equal to m times the wavelength, where m is just some integer. Cool? Now what I want to do is I want to be able to predict where that bright spot is going to show up. So from the center of that point where I drew that imaginary line to where that bright spot strikes, we're going to call that y. Okay? We're just going to call it a distance, and I don't want to use d because I've already used d over here. So I'm just going to call it some distance y. Okay? So that distance y, if you take it back times r, or sorry, that distance y, this distance r, is talking about, is going to create an angle from this line to there that's equal to theta. Okay? So I can say that my brain isn't working really hard. Oh, that r over y, sorry about that, my brain is giving out. This angle over here, so that's going to be y over r. So tan theta is equal to, well, tan theta is equal to opposite over adjacent, sorry, which is y over r, not that r, that r. Okay? And now that theta is not exactly the same as that theta, but it's close enough. Okay? Now, for very, very small angles, I can do a substitution. For very small angles, I can say tan theta is about equal to sine theta. So I'm going to make a substitution here. So this only works for very small angles. So you want to have this distance great compared to this distance. If this distance is short compared to this distance, you can't make that approximation. So that means that sine theta is equal to y over big R. Cool? Well, sine theta times d is equal to this. Well, I'm going to divide that by d. Okay, so I'm left with, and now I'm done with this area. If you need this area, I'm going to erase it because I need the space to work on a few problems. If you need to relook at it, just rewind the video. Right. Okay? Got dead space going on. So I end up with d sine theta is equal to one wavelength times some number n. Let me rewrite that so you can see it. Cool. We also have this relationship of tan theta is equal to y over r. Now y was the distance from here to here. This r was a big R, which is the distance from the screen to there. So what I can say here is that sine theta is equal to m over or m times the wavelength over d. Okay, and then I can say for very, very long distance, from this to this being huge compared to this, that tan theta is pretty much equal to sine theta. Okay? Now, if I do a substitution, I end up getting m, which is an integer, 1, 2, 3, 4, 5, times lambda over the distance in between the two holes is equal to y, which is the distance from here to that bright spot, divided by r. No, not that r. Big R. Can you see that? Yeah. Where big R is the distance from here to here. Okay? So now I have my equation for interference. Cool? Now what if I wanted to say that was not constructive interference but destructive interference? Well, the principle is still the same, except this has to change. Okay? We say instead that it can't be one full wavelength, it has to be a half a full wavelength. So what we can say is that it's going to be 1 plus a half m lambda. No, sorry, mistake. That's what I wanted to say. Okay? So if it's 1, it goes through 1 1/2. If it's 0, it goes through a half. So if it's 0, it's this point. If it's 1, it's 0 this point. 1, it's this point. 2, it's this point. On and on and on and on. Okay? So once you've done that, you're just doing a substitution in for m. Okay? So instead of your equation being m lambda over d equals y over r, for destructive interference, you're going to end up with m plus 1 lambda over d equals y over r. Okay? So this is for constructive. That's for bright spots. And this is for dark spots. Okay? So I'm changing it by a half a wavelength to get destructive interference. This one, it's full wavelengths to get constructive interference. Bright spots, dark spots. That's the double slit experiment. Cool?